The molecular compounds are the compounds that are made of molecules like glucose, and they dissolve in water, but they don't form any ions when dissolved in water. So the glucose just changes from the glucose which is in the solid form and changes into the glucose which is aqueous or so dissolved in water, but no ions are formed. Most molecular compounds remain molecular when dissolved in water, and some molecular compounds like HCl acids, they hydrolyze or break down into ions when dissolved in water, like hydrogen halide, hydrogen chloride, hydrogen fluoride, H2SO4, and HNO3 are all uh, molecular compounds, but still they form ions inside the water. While the ionic compounds all make ions inside the water, ionic compounds are made from metals and non-metals joined together. So sodium bromide is made from sodium metal and bromide non-metal. When they are found in any aqueous solutions, so a solution which is made from water, they will break down into the ions Na plus and Br minus. So they form something which is called electrolytes. The definition of an electrolyte is something that dissolved in water, break down into ions, and they conduct electricity. Even if they do this partially or to a small extent, they are still known as electrolytes. The periodic table can be used to predict the electrolytes from a list, so I can know the metal and the non-metal, and then I can join them together to make the ionic bond. The cations are the positively charged ions, and the anions are the negatively charged ions. All soluble substances are substances that dissolve in water to give a concentration which is at least more than 0.1 molar. So if you have a solid which is dissolved in water and give a very small concentration, less than 0.1 molar, then it's not considered as soluble. If it is equal to or more than 0.1, then it's known as a soluble substance. When it dissolves in water, you don't see it anymore, and there is only water inside the test tube or in your flask. We can have some solubility rules that will help us to know if the substance is dissolved easily or not. So I know that all the ammonium salts, so any salt that starts with the ammonium ion, or the sodium salts, or the potassium salts, or the lithium salts, all the nitrate salts which ends with NO3 minus, and all the acetate salts which are made from the salt of the acetic acid or ethanoic acid, they are soluble in water. Whatever was the ion that's found in them in their compound. The chlorides, the bromides, and iodides are all soluble in water, whatever the ion they are combined with, except only if they are combined with silver and copper and lead too, in which cases they are insoluble. Any compound that contain a sulfate ion is soluble, except the strontium, the barium, and lead, and these are all insoluble exceptions. Calcium 2 plus is, yes. The sulfides are insoluble, except for if they are combined with one of these ions, that's known as rule number 1. And if the sulfides also is combined with beryllium or magnesium or calcium or strontium or +2 EA, in which they are known as insoluble salts. If you find the solubility rules are very difficult, don't forget to look for our solubility rules notes in the form of one PDF page found inside this course. The hydroxide and the oxides and the phosphates and the sulfites and the carbonate ions are usually insoluble, except for the rule 1, which is soluble salts. I can use these rules to find the solubility of any given compound and to know if a precipitate will form upon mixing two given solutions. And we need to know the colors of some of the compounds also. So all group 1 salts are white and their solutions are colorless. All carbonate salts are white except for copper carbonate, which is green. All sulfide salts are white except for copper sulfide, iron sulfide, and lead sulfide, which are black. A green precipitate is due to mostly iron 2 ions like iron hydroxide. A reddish brown precipitate is usually due to iron 3 salts like iron hydroxide. A barium sulfate is a white precipitate. A silver chloride is a white precipitate. A silver bromide is a creamy precipitate. A silver iodide is a yellow precipitate. A copper hydroxide is a blue precipitate. A lead 2 chloride is a white precipitate. A lead 2 bromide is a white precipitate, is a creamy precipitate. A lead iodide is a yellow precipitate. If you notice, this is the same colors that are with the silver. The lead hydroxide, PbOH2, is white. The aluminum hydroxide is a gelatinous white, and zinc hydroxide is white. The flame tests are the tests which are done when you put a flame cleaned by acid inside some solid, and then you put this solid in a flame, and using the flame will produce different colors from which you know which metal you have used. So if you have lithium, that will make a red flame. If you have sodium, it will be a yellow-orange flame. If you have potassium, it will be a lilac-violet flame. If you have calcium, it will be a brick red flame. If you have copper, it will be bluish-green flame. The test for halide ions using silver nitrate followed with ammonia. So I have silver nitrate to be added to chloride, will form a white precipitate. To bromide, it will form a creamy precipitate. Iodide, it will form a yellow precipitate of silver chloride, silver bromide, silver iodide solids. And you need to know how to write the equations of these. The test for ammonium is the test using sodium hydroxide and heat, and it will produce ammonia gas, which can be found as a pungent smelling gas, and it turns the wet red litmus paper into blue because ammonia is a basic. And the nitrate has exactly the same test for sodium hydroxide and heat added, but the difference is that you put some aluminum foil will produce also the ammonia gas. The test for aluminum is by addition of sodium hydroxide till in excess and adding of ammonia till in excess. Then aluminum, zinc, and lead will make different results. Together with calcium, some of them will produce white colors. And in order to differentiate between them, we have either to put the sodium hydroxide dropwise first, or we can put it in excess. And we can also put the ammonia solution first dropwise, and then we can put it in excess later. Every one of them produces white precipitate, but in different methods with these two reagents. So we have to compare the calcium, the aluminum, the zinc together. Upon addition of few drops of sodium hydroxide to calcium, it will make a white precipitate, and when we add excess, it does not dissolve. It remains white. If we add it to the sodium hydroxide, few drops to aluminum or zinc, it will make a white precipitate that dissolve in both cases, so there is no precipitate if I put excess. It will make a dirty green color in case of iron Fe2+, that does not dissolve in excess and stays as a precipitate. If it will make an orange brown or reddish brown with the iron 3, if you add excess, it does not dissolve also. It will make a pale blue precipitate which does not dissolve with excess sodium hydroxide if it is a copper ion, and it will remain as a pale blue precipitate, and a light green with the chromium ion that does not dissolve in excess also. Because you cannot differentiate here between aluminum and zinc ions, both of them forms a precipitate that dissolves in excess with sodium hydroxide. You have to use another reagent. The other reagent that you need to use is ammonia solution. The ammonia solution is very similar to the sodium hydroxide test, but there is a little difference is that there is no precipitate at all when you have calcium ions for no white precipitate. In case of aluminum ions, the white precipitate with the ammonia solution in H3 aqueous is going to form and it does not dissolve with excess. In case of zinc, it will form a white precipitate that dissolves. The same color is almost for green, dirty green for the iron 2, dish brown for the iron 3, and pale blue for the copper, and light green for the chromium. The only difference is that the pale blue precipitate with the ammonia solution dissolves. The precipitate dissolves and forms a deep blue solution. And the light green precipitate dissolves and there is no precipitate, becomes colorless solution without precipitate in the case of chromium. So again, to differentiate between the aluminum and zinc, you need to put the ammonia solution in H3 aqueous. It makes a white precipitate with both of them. It dissolves in case of zinc in excess and does not dissolve in excess of ammonia solution and does not form a white precipitate at all with calcium. The same colors with ammonia solution as with the sodium hydroxide solution previously. A green precipitate here, orange, reddish brown, pale blue precipitate, light green precipitate. In case of excess, does not dissolve for Fe2+, does not dissolve for Fe3+, dissolves and changes from a blue precipitate to a deep blue solution, and dissolves to form a colorless solution without precipitate in case of chromium. Test for carbonate and bicarbonate effervescence to give gas carbon dioxide. They are easily identified with the lime water, and sulfate with the barium nitrate forms white precipitate of barium sulfate. As we said, ammonium and nitrate are tested the same way. The only difference is that nitrate, you put solid aluminum, like aluminum foil, together to form the ammonia gas that can be tested. So solubility is the molar concentration of the saturated solution. This is the maximum amount of solute that can be dissolved in 100 grams of the solvent like water. If the solution is said to be saturated, it means that you cannot dissolve any more amount of solute in this solvent at this given temperature. Solubility of most solids increases with increasing temperature. If a saturated solution is having a maximum amount of solid and then it's cooled, the solid will precipitate out. We can use the solubility curve to find out the increase in solubility when the temperature is increased and find out the mass of the solid formed when a saturated solution is cooled. Determine the mass of water needed to dissolve a specific mass of solid at specific temperature, and determine mass of solid but that will dissolve in specific mass of water at specific temperature. Any insoluble solid is always in equilibrium with its ions in solution. So if I have silver chloride, which is insoluble, it has equilibrium with its silver ions and its chloride ions in its solution. Because this is very insoluble solid, so mostly the equilibrium goes to the left, where the silver chloride is much more than the silver and chloride ions. So instead of using K equilibrium for the equilibrium, we can use a KSP, which is called the constant of solubility or the solubility product. The solubility product can be found in the same way like the K equilibrium by dividing the products over the reactants, and it's equal to the concentration of the products multiplied by each other, and everyone is raised to the power of the coefficient. And since silver chloride is solid, it can be entered in the equation. The larger the KSP value, then this means that the solid is very soluble. The lower the KSP means that the solid is not soluble. When a solid gives ions in the form of ratio of 1 to 1, like Na divides into Na plus and Cl minus, the K product of solubility is equal to the solubility squared, or the concentration of each of the two ions multiplied by each other. If it is giving like calcium chloride to the ratio of 1 to 2, like calcium gives the ratio of 1 to 2, then the KSP is calculated by 4s cubed, and S the concentration of one of the ions or the solubility. And if it is to the ratio of 1 to 3, like aluminum is 3 plus and this is 3 OH minus, so the ratio is 1 to 3, then the KSP is given by the equation 27S4. And if you have the S and you want to find the KSP, So S is equal to the radical of KSP, and here the S is equal to radical 3 KSP over 4, and the solubility here is equal to radical 4 KSP over 27. When I have two solutions mixed together, the solubility of them makes difference in the concentration of the produced solution due to change in the volume. So if I have 50 milliliter added to 50 milliliters, the new solution is 100 milliliters, so the concentration of the ions now becomes different. If I want to compare the value of Q at any point versus the KSP, it will allow me to know if there is an equilibrium or no. If they are equal, then it's at equilibrium. If Q is more than KSP, so the solution tends to go towards the solid and forms a precipitate, while if the opposite happens and the Q is less than KSP, so solution tends to go towards the silver and chloride soluble ions, and it does not make a precipitate. We can use this information to also calculate the concentration of ions left after a precipitation reaction and calculate the mass of precipitate formed when two ionic solutions are mixed.